So hello everyone, many thanks for the invitation. I'm happy to present here some of the results we've published recently concerning surface process response to normal fault growth during single and multi-phase rifting using a numerical modeling approach. I would like to acknowledge my colleagues, of course, who helped on this, and also to say that this work was designed to a great extent by the late Patience Cowie, who I guess many of you know here. So in this first slide, we are looking at a model rift topography that evolved in response to multi-phase extension. The purpose of this work is to understand how erosional and depositional processes evolve in rifts that are characterized by complex multi-phase extensional histories, and to make a comparison to simpler single-phase rifts. So I will start by saying that understanding surface process response to tectonics in multi-phase rifts is trivial. And this is because the topography and the stratigraphic patterns that are associated with the older phases of extension are usually overprinted by the subsequent extensional phase. And the slide here, you're looking at a hillside map from an active rift in northern Greece, the Mygdonia Rift, that evolved in response to two phases of extension, a northeast-southwest extension during the Miocene and a north-south extension during the Quaternary. So understanding surface process response to fault growth in this area is a bit trivial. For example, if you look at the southern parts of this rift, sediments that were deposited on the hanging walls, so the first phase faults, if you see them here with yellow color, are now being incised on the uplifting footwalls of the second phase faults that you see with red lines here. So our objective is to investigate the geomorphic and stratigraphic evolution of rift basins that are subjected to both single and multi-phase extensional histories. And we do that by quantifying the magnitude and the distribution of surface processes during multi-phase rifting, and by making a direct comparison to single-phase rifting. In particular, we look at the drainage network evolution and the location of the main drainage divides across the developing rifts. We investigate spatial and temporal variations in sediment supply and the implications for simple stratigraphy, and finally observe any shifts between erosional and depositional processes during fault growth in both single and multi-phase rifts. So we follow a methodology where we use two numerical models, a tectonic model and a surface process model. In particular, we use rift-related topographies from a tectonic model that are read as input files into a surface process model. Keep in mind that this is a one-way coupling modeling approach. This means that sediments do not affect fault evolution. And although we acknowledge that this is not always the case, and many studies have shown otherwise, in our case, this is considered of a minimal issue simply because we are not creating sufficient space to accommodate large sediment volumes that would have an impact on fault evolution. So we use output from the tectonic model of Finch and Gawthor, published back in 2017. This is a 3D discrete element model that simulates an accretion, propagation, and linkage of normal faults. In this model, the continental crust consists of these spherical elements, which interact in the upper crust through linear elastic repulsive attractive forces, whereas in the lower crust interact through linear viscous forces. Faults develop spontaneously and are defined as pairs of broken bones between juxtaposed discrete elements. And once a bone breaks, it's not allowed to heal. In our study, we used output from two experiments, one where fault development occurs in response to a single phase of extension, and one where fault development occurs in response to two non-collinear phases of extension. In the slide here, you're looking at a 3D view of the multi-phase model after 4.5 million years. With arrows here are the extensional phases that have 60 degrees angle between the extension directions. 30 by 20 kilometers are the dimensions of the model, and with orange here, you are looking at the fault scarps. Also in this slide, we can see how fault development occurs in this tectonic model, with black to gray areas as the fault heave, and the maps behind are subsidence uplift maps. In the upper panel, you see the single phase rift. In the lower panel is a multi-phase rift, and yeah, this is time. So in the single phase rift, fault development occurs in response to north-south extension only. You see the amount of extension here. So at the beginning of this experiment, we have a large number of small faults which gradually propagate and link perpendicular to the extension direction. In contrast, in the multi-phase rift, we have first a period of oblique extension and then a period of north-south extension. So in this case, we have inherited faults from the first extensional phase that grow in response to the second extensional phase, the north-south extension. Also, we have new faults that are forming. So if you look at the 4.5 million years here, we see these characteristic zigzag fault geometries that emerge because of the link that's between first and second phase faults. If you want to look at more into how this fault development occurs, there is a paper coming out by Finch and et al. That's now in preparation. So in our study, we compared the geomorphic and stratigraphic evolution of these two rift systems after equal amounts of north-south extension. The rift topographies that we use from the tectonic model are read as input files into our surface process model. We use a code by Badlands. This code uses a mass balance approach to allow sediment transport and deposition under varying tectonic and climatic forcing. River erosion is modeled by the stream power law, where erosion rate is proportional to the erodibility coefficient times the upstream drainage area times slope. In our simulations, we use a constant precipitation rate of 1 meters per year, a spatially uniform bedrock erodibility, and we kept the base level constant at 0 meters elevation. So now I will show you two videos that show how the single phase and the multi-phase rift evolved for a period, the total period of 5 million years. So as faults grow in both experiments, maximum footwall relief increases, hacking coal subsidence is created, and we see these grabens or half grabens forming that in some cases are getting filled with sediment, and in other cases are going into underfilled or sediment-starved basins. So now let's look at this in more detail. This is the topography after 5 million years for the single phase and the multi-phase rift experiments. In these maps, with black lines, you see the faults, with black dashed lines are the main drainage divides, and with blue lines are the main rivers. So what we can see from this is that in the single phase rift, there are large axial river systems which flow parallel to fault strike, and relatively small transverse catchments like this one, for example, that drain the uplifting footwalls. In contrast, in the multi-phase rift, we see the development of more complex drainage network patterns due to the linkage of the reactivated first and second phase faults. You can see these characteristic hook-shaped drainages here and here. And overall, we see the formation of larger drainage catchments compared to the single phase rift, like this catchment, for example. A key characteristic in both experiments is the very dynamic evolution of the drainage network. So in both experiments, we see that drainage intergrades either due to fault linkage or due to basin overfill and overspill. We also see the opposite effect of drainage integration, that is drainage isolation and the development of eternally drained basins. So I will show some examples of this. This is a zoom in this area here in single phase rift at 2.5 million years. We see these initially isolated basins. You can see the cross-section here that goes from X to Y. So after 500,000 years of model run, due to surface subsidence in the area of fault linkage, this leads to basin integration between these two basins. Now you see the orange profile. Then at 3.5 million years, if you look at this basin here, this is getting filled with sediment up to the height of spill pond, leading to further drainage integration. So now you can see the red profile. The opposite effect is observed at 5 million years, where due to rapid surface uplift caused by fault interaction in this area, we see the drainage isolation and the development of this internally drained basin, that one. Overall, we see that there is a gradual increase in the hydrologic connectivity of the drainage network in both experiments as faults become progressively linked. And here you're looking at erosion and deposition maps after 5 million years again for the single phase and the multi-phase rift experiments. With red here is deposition and with green is erosion, and with black lines are again the faults. And in these two diagrams, you can see how average erosion and sedimentation rates vary with time. For the multi-rift experiment, you see the red line in these diagrams, and for the single-phase rift experiment, you see the blue line. So what we can see from these two is that both erosion and sedimentation rates are higher during the multi-phase rifting. This relates to the inheritance of structures from the first extensional phase, which what they do is to accelerate the accumulation of topographic relief, thus resulting in higher erosion and sedimentation rates.
Sorry to interrupt, you have 10 minutes now.
Yes, thank you. Another difference between these two experiments is in the single-phase rift, you see small to medium-sized deposenters, you see them here, that usually grow into overfilled or nearly filled basins. In contrast, in the multi-phase rift, we see more of a deposenter merging, which leads to the development of these larger deposenters that usually become underfilled. So we'll show you two examples. This is from an underfilled basin from the multi-rift experiment, and this is from a nearly filled basin from the single rift experiment. So what you see here is how accommodation space varies with time, the black line, and sediment supply, the gray line. So in this case, accommodation space overpasses sediment supply. So this basin is sediment starved after 5 million years of model run. Whereas here, accommodation space almost equals sediment supply after 5 million years. So that's the reason that this basin is nearly filled with sediment. Another interesting thing to look at is basin stratigraphy. These are two cross-sections that are going through the main rift epicenters from north to south. I just choose to show you this because I think these are quite representative. In these cross-sections, colors represent sediment age. With white to purple colors are the younger sediments, and with brownish to yellow are the older sediments. So what we can see from this is that there is a limited sediment accumulation during the early stages of single-phase rifting, whereas in the multi-phase rift, sediment accumulates from the early stages of the second extensional phase. You can see these older sediments deposited here and here, for example. Another difference is that the stratigraphic patterns in the single-phase rift are usually characterized by gradational stacking, whereas in the multi-phase rift, we see the incomplete stratigraphic records, like here, for example, and the reworking of sediment. And this is because there is a shift from an area of deposition to an area of erosion. So this area used to be an area of deposition that's now it's being eroded, possibly because this fault became inactive and we have a new fault forming here. Also, in the single-phase rift, sedimentary phases should shift from marine lacustrine to fluvial, because, as I mentioned, most of the basins are getting filled with sediment. In contrast, in the multi-phase rift, sedimentary phases should shift towards the lacustrine or marine conditions, because these basins remain underfilled. Finally, if you look at the individual deposenters here, we can see that there is a temporal variability in sedimentation that reflects changes in the upstream drainage area that are due to drainage reorganization events. So in these plots here below, this is cumulative sediment thickness versus time for deposenters A and B in the single-phase rift and C and D in the multi-phase rift. What we see is that we see increases sediment thickness that relate to drainage area gain. You see these symbols here. And this drainage area gain is due to drainage integration events. So to summarize the highlights, in both of our experiments, we see very dynamic drainage network evolution where fluvial connections established between adjacent basins. We also see the opposite effects towards drainage isolation. This drainage reorganization has a direct impact to sediment flux and accumulation rates. Overall, we see higher erosion and sedimentation rates and the development of larger syn-rift deposenters during multi-phase rifting, where we also see the shifts from erosion to deposition that they are not so often in the single-phase rift. And finally, there are differences in the syn-rift stratigraphic development between these two experiments. And I would like to close with some ideas for future work, and that is to compare our modeling results to natural examples of multi-phase rifting, and I'm happy to hear any suggestions, and also to perform sensitivity tests to explore the effects of, for example, using a spatial variability in petrogradability. Many thanks for watching.
Excellent. Thanks a lot for this nice talk. We are a bit late. It's already 5. Some have to leave. I'm sorry for that. But there's, I think, still time for questions. And if there's none, I will just start. I'm curious.
Yes.
If you have multi-phase rifts, you in a way change the degree how much the rift is ordered, because then you get different fault lengths, you get different fault connectivities, you get different catchment sizes.
Yes.
And how much does this depend on the obliquity that you impose? Because this is the parameter that controls how much multi-phase you actually have. Yeah. And
you mean how much? Yeah. Okay. So in our study, we use a 60 degrees angle between the two extensional phases. And I know, but I didn't show here. But of course, this can really change if we use a different angle between these two extensional phases. So there is an impact, but this is something that we actually want to quantify in a future study because, well, I mean, there is plenty of room to do many model runs, many simulations, but yeah, this is definitely, I assume that it changes a lot. Surface processes respond a lot to that, but this is something remains to be shown in the future.
Okay, then I'm looking forward to see what you find out about those in the future. Any other questions?
I have a quick one.
Oh, yes, yeah, go ahead.
Okay, thank you very much for this talk, Sofia. It's really exciting and interesting result. So my question is that your model assumes a wide drifting scenario. And I'm wondering that, you know, in the narrow drifting scenario, you could also have the same observations that you show here for not all of them, but a lot of the observations that you show for the wide multi-phase scenario here, you can have the same for single phase narrow rifting in the sense that you have two isolated rift basins, you know, assuming you have multiple segments, and over time they, you know, propagate, the faults link up, and you have, you know, basins that become open to one another. You can have the same result without necessarily changing the orientation of extension, you know, single phase, single extension direction over time.
Yeah,
can have the same.
No, it's I just wanted to say, sorry for interrupting your question, but in these experiments, actually what we assume is that we have a pre-existing topography in the multi-phase rift experiment. And this is a difference from the single phase rift. Yeah.
Yeah, but so again, my question is about the setting itself.
Yeah.
So here your experiments seem to me to be most valid for wide drifting, multi-phase versus single phase rifts, and not necessarily for narrow rifting, multi-phase versus single phase rifting. Do you get my point?
Yeah. Well, to tell you the truth, I haven't really thought about that. so yeah, I mean, I don't really know. Yeah. What's the answer to that question?
No problem, but exciting results. Thank you.
Yeah, thank you.